Bodo and Lorelei, I'm going to let you introduce yourselves.
Hi, everyone. So I'm Bodo, and
I'm Lorelei.
And this is Lorelei. So we want to share a quick story, and I'm going to present something. So can you guys see the screen?
Yes.
So when Lorelei was about 5 years old, over the span of just a few hours, she suddenly became paralyzed, and she lost about 80% of her movement. She couldn't sit up, she couldn't walk, she could barely speak. Her breathing was really weak.
I couldn't even swallow.
You couldn't even swallow, yeah. And so her whole body was starting to be paralyzed, and this happened over just a matter of a few hours. And I want to tell you a story of how we ended up using that situation to build her a brain-controlled robotic arm that helped her left arm move again. And that's the story I want to try and share with you today. So what was really cool is that Lorelei has always been very positive, very happy girl, and this was her about like 7 to 10 days after she got to hospital. At this stage, she had regained a lot of her strength, but her left arm was completely paralyzed, completely damaged, and she couldn't move it. And there was very little hope for any recovery. The damage to the motor neurons was permanent. We found out that the disease that she got was acute flaccid myelitis, which is a cousin of the polio virus, and it's a very rare condition. It's becoming less rare suddenly nowadays, but she was one of the first to get this. What we discovered while we were in that hospital was that about 100 or so kids around the world had got this, and most of them were still on respirators, were still in the hospital. Those that had paralyzed limbs still had paralyzed limbs. And we didn't know what to do. So while we were still in the hospital, we discovered these projects that were building exoskeletons. And what was interesting with these exoskeleton projects was that they were trying to get brain signals to control the exoskeletons so that the brain, first of all, doesn't forget how to send signals to the muscle, but then also, helps with the movement. And then over several months, that movement would start to rehabilitate her motor neurons. So we reached out to these companies and to these projects, but they were all closed. They didn't want to share what they were doing, or at least those that did want to share, they were quite insistent that we pay them quite a lot of money, which we didn't have. So we decided that we're going to try and build our own, and we had no idea how to do this, but we thought, well, let's think about the problem. We need to get some solution for an arm brace. Then we need to figure out how to create this actuator to pull her arm up and down, and then we needed to try and figure out how we can get signals from her brain to control the exoskeleton. And so what we started to do was, because we didn't know how to do any of this, and I guess we still don't really today, but we recorded a bunch of videos, and we asked different people different things, and different communities different questions, like how do we 3D print, what are the mechanics behind this? And very quickly we got people from all around the world helping us. Some of those are on this call today. And so random people from South Africa and Namibia and Germany helped us with the electronics. Friends from California helped us with the 3D scanning of our arm. We had companies donate a whole bunch of actuators. We had students help us with the designs. And then what was really cool is that this was us This was us a few days after coming home from the hospital, and we started to work on this and started to work on all these cool little parts of the project, and we were learning as we were going. After about 6 weeks or so, this was our first prototype. It was made.
It really pinched.
It did, yeah.
I didn't really like it that much.
No, this one actually really did hurt her arm. So we quickly demolished that. A few days later, we had built this one was pretty good. Well, this one was a lot better.
It pinched a little, but it was much better than the last one we had.
Yeah. And every time we presented a question to the community, people would come back with answers and helping us, figure out certain parts of the puzzle. And we started to document all these parts on an open wiki site, which is available to everyone. And this is some of the. So what we wanted to do was we wanted to encourage other parents, like those 100 other kids that were in Lorelei's same position, to also do this with us. And so we had these instructions. These are just some examples. We learned how to 3D print, and this was us getting our first 3D print, us putting it all together. But up until this stage, things were progressing pretty quickly and nicely. But we had this one big challenge: was we were trying to get signals from her brain to control the exoskeleton, and we couldn't use off-the-shelf muscle sensors or anything like that. We really struggled with this. The idea was that if we could get some signals from the arm, and this is a representation of what the signal looked like from my arm, then we could normalize the filter and put a threshold on it, and then when I pull my bicep, when it picks up that threshold, we could get it to move the exoskeleton. Right. So this worked really well for me, but it didn't work for Lorelei. We just couldn't get the signal from her arm, and it was crazy. When we put a threshold on this type of signal, it would have been triggered by her heart beating or maybe a finger twitching. So it was very erratic. It didn't work at all. And so we recorded another video, and this time we reached out to a different set of communities who were specialists in signal processing. And then through the help of community, we figured out that, well, instead of just looking for one signal, let's get as much of the signal data as we can. Let's push it through some machine learning. And then here you see it working. It's controlling. So even though Lorelei can't move her arm, we're getting enough signal through these. I think we had 18 sensors or something.
It was a lot.
We had, and we got enough signal through that we could train some machine learning algorithms to pick up the different signals and then control a virtual arm. And this was all thanks to the community. And then at this stage, other people around the world started to take the designs from the website and started to build their own. And then we went. I think this was us in Geneva. We got invited to Geneva to work with Google on some of these arms. But it was really cool. I mean, this was a really fun project. And then this was us again in Geneva. These are all guys who work at CERN. So these guys are, making black holes during the day, and then on the weekend they helped us to figure out some of this project. But what was really cool is that over the course of several months, we started to figure out this problem and build this device. And from a very early time, we kept forcing Lorelei to send signals to her arm so we can try and pick that signal up. And then we eventually got it working. But all this time, she didn't forget how to use those muscles. And even though she had this exoskeleton, which gave her like an external muscle, which did most of the work for her, her muscles were starting to do a little bit of the work. And then at Christmas time, or just shortly before Christmas, she comes up to my wife and I, and she says, "Hey guys, guess what I can do?" And she goes and she shows us that she can move her arm. I mean, now she's doing it a lot better, right? Now and show how you can hold it. Yeah.
Could you turn off your screen for a moment so that we can see you better?
Oh, okay, yeah. Let me do that again. Can you show us again? So she's able to use her bicep really, really well. Her tricep isn't that strong. So her biceps regained 60%. Now, we haven't figured out how to solve this problem with her shoulder. So her shoulder's still paralyzed. But yeah, I mean, it's really cool that people from around the world helped solve this challenge. And now this device is freely available for anyone to build. What would have costed us about $100,000 is now available for like $100. And okay, it's not perfect, right? This thing always fails, especially today because I forgot to charge the battery. But yeah, I mean, it's cool. It's all open source, and what we hope is that by openly documenting it, more and more makers can take it, one step further, 2 step further, 3 step further, and hopefully it becomes something cool. Yeah.
Fantastic.
Yeah. Was it a fun project? Mm-hmm. Yeah. And so now she goes all around to different people and schools and talks about it when she's not too shy. Yeah.
So early on, you were trying to figure out what was happening. And what helped you with even just bringing words together to describe what was going on? And did you start collecting allies just to become your mentors or to be self-advocates? So what's the process from going up from self-advocacy to becoming an advocate for others and sharing your solution with others? What is that like?
So we well, first of all, we didn't think any of this would succeed. So we broke down the project and we thought, okay, well, let's just try the first step, and that is 3D printing. And we were both interested in 3D printing. It was cool, right? So okay, let's try and build this 3D arm brace, and then see if we can, maybe that's the limit of where we go. And so we reached out to the Naval folks and to various other guys, and they helped us 3D print. And then while we were doing that, we got in touch with some students who were doing mechanical engineering, and we asked them the question, well, how do we design a joint so that, because the torque on this isn't all that strong. So we needed to design the joint so that we maximize the torque that's available so that it can pick up per arm. And so a bunch of students helped us figure that out. And it's all these little problems, like we first wanted to 3D print this in its form. And well, we did that, and then we couldn't fit it onto our arm. And then some Enable folks said, oh, wait, you should print it in PLA, and then you can mold it with some heat. And so it's little problems like that we didn't even know how to articulate in the beginning. But every time we had a problem, we said, okay, listen, guys, this is where we're at. We don't know how to get the next step. Can you help with the next step? And I think that's what made it work really well. Is you don't go to someone and say, hey, listen, I want you to build an exoskeleton for us. It's more like, hey, we don't know how to do this little step. Can you help us with this little step? And then we document it and share it, and then other people commented and said, oh, I've got a better idea, and this is how you do it. It was really cool.
You're working with some highly qualified professionals. When you're talking about CERN, you're talking about the people who, as you said, are making black holes by day, right? And calculating your physics problems by night. What is that like?
No, I think it snowballed really quickly to that, and it was just interesting. Like it just snowballed, and I don't know how that happened. It's all just serendipity, or